Okay, let's get started. As you're probably aware, today is Veterans Day. I grew up in Canada where it is known as Remembrance Day. And in Canada, like the other Commonwealth countries, there is a tradition where at the 11th hour of the 11th day of the 11th month, everyone pauses and takes a minute to remember. So that is in about 10 minutes time. So we will do some HCI for about 10 minutes, and then we will pause for a minute to remember those who made the ultimate sacrifice to try and make lives better for others. Okay. All right, back to HCI. I made a change to the grading outline. If you'll remember, this used to be 10 deliverables worth 50% and a final project worth 15%. My experience in previous years is between now and the exam period, when the final project was due, not a lot happened until the night before. So we're going to have 3 weekly reports. And to try and give you a little bit of a break, the first report, as you'll see, is worth 5%. And it will replace your worst deliverable. If you do not have a worst deliverable, I will think about some other way to make it up to you. I think we'll use it to replace your worst quizzes. If you don't have a worst deliverable or any missing quizzes, I'll think harder. I don't know if there are any students in that situation. But anyways, report 1 is to help you make up for some points you may have lost along the way so far. I've then taken 4% out of the final project and distributed it across written report 2 and 3. Sound good? Sound fair? Okay. All right. That's up there on the syllabus if you want to have a look at the details. So back to the schedule. So again, you're working on your weekly report now, which is due at the normal time, 11:59 p.m. on Wednesday. Remember, there are 3 parts to this written report. Part 1 is you're going to be outlining a use case. Your user turns on the system. The system presents this visual output. The user does this. The system does this. The user does this. Back and forth. So we can you can sketch out for us how your system is going to unfold, how the interaction with your system is going to unfold over time. Second section is you're going to be talking about measurables. What are you going to actually measure as you're sitting next to your user and watching your user interact with the system? Part 3 is you're going to talk about when you actually do this user testing and collect all those measurements. Depending on what those measurements say, how will that point you back into your system to make improvements, right? If your users score low on this metric, where in your code do you think you need to go to make improvements so that at the next round of user testing, users will score high on that metric, right? So we're doing all of the preparation to get ready for user testing, which you're going to do over the Thanksgiving break. Any questions about report 1? No? Okay, so let's carry on with our section on looking outward. So far in lectures 15 through 19, we've been talking about embedded devices, which are devices that are out there and can directly sense the world. But unlike us embedded devices, they cannot move about and they cannot generate their own sensory stimulation, right? So we've talked a lot in this course about interaction being pushing against the world or pushing against a system and observing how the world pushes back. Embedded devices can record, but they cannot push, right? They can't actively influence the world. So in lectures 20 through 24, we're now going to talk about this emerging class of technologies, which is only just now starting to enter our everyday experience, which are robots, which, like us, have motors with which they can push against the world, and they can observe the sensory repercussions of their actions. If you go work for an HCI production house, you might not necessarily be working on autonomous robots, but there are a lot of other HCI technologies that are coming down the pipe that have this same sort of property. 3D printed prostheses is one example. We're going to talk about, in the very last lecture of the course, we're going to talk about brain-computer interaction. So a lot of these emerging technologies have this similar property that either autonomously or together with a human, they can influence the physical world and observe how the world pushes back. Okay. Okay, so let's talk a little bit about robots. So I want to start with our little cartoon here, which is, in this case, a robot, R, which has some output, so it spins its motors and it has some influence on the environment, and then through its sensors it receives some input and it can record the sensory repercussion of that action, right? So all of the robots we're going to talk about in the next 4 lectures, no matter how sophisticated they are, this is basically what they're doing, right? Now, E, being the environment, could be the physical world, it could be another robot, or it could be a human. And I'll skip back to the schedule for a moment. So you'll see that we're going to talk about robots, then we're going to talk about human-robot interaction. So E is replaced with H. A robot is interacting with the human reacts, and the robot observes that interaction. And then we're going to talk in lecture 24 about robot-robot interaction. So what happens if the output of one robot becomes the input to another robot, and vice versa. Okay. While the robot is interacting with its environment, we of course have a human observer over here, which is observing or receiving as input. We are observing this interaction. And I want to start with the observations from the point of view of the human. And these little cartoons here are from a book we wrote on the subject a few years ago. One of the biggest challenges in robotics is when you're observing a robot or observing an animal interacting with its environment. Remember, the brain is a prediction machine. It's building up a mental model of what is going on inside the robot or the animal or the other human. We tend to anthropomorphize, right? Remember, we were talking about Jibo, and Jibo sees, and Jibo is enjoying the interaction. One of the repercussions of anthropomorphization is we often think there is more going on inside the animal or robot that may actually be going on, right? So what I'm going to try and do as we move along here is help you check this natural instinct to build up a more complicated mental model that might actually be there. In robotics, we obviously take inspiration from the natural world, from humans and animals, and we try and take what we think is going on inside an animal or human and build that into a robot. And often that gives us an overly complicated machine that doesn't work. And in my opinion, that's why robotics research has been so slow over the last 60 years compared to computers, which have advanced way beyond robotics. Both robots and computers started right at the end of the Second World War. One of the things that has held us up in robotics is we've had the wrong mental model. We've been trying to build the wrong mental model into our robots. Okay, I see that it is 11 o'clock, so I want to pause and just take a minute to remember those we've lost in the various world wars. Okay, thank you. Okay, let's continue our discussion. We're talking about humans who are building up a mental model of what animals or humans are doing when they interact with the physical world and trying to build that into machines. And as our little cartoon shows here, this often doesn't work. So what's the alternative? The reading for today comes from an alternative that was proposed by Valentino Breitenberg. Breitenberg was a neurophysiologist, so he studied the brains of animals. Breitenberg wrote a book back in the 1980s called Vehicles. And before we talk about his book, I want to talk a little bit about his research. Breitenberg, among other animals, studied the fruit fly. You know how big a fruit fly is. Fruit flies have brains. They're pretty small given the size of their body already. So the brain of a fruit fly is exceedingly, exceedingly small. Despite that, they're pretty sophisticated animals. This is usually specifically true in student apartments. There is some food that is perhaps past its due date, and these little fruit flies start to appear. And if I had a little bottle of fruit flies here and there was a piece of rotting fruit in the back corner of the room and I opened it, they would do a pretty good job triangulating on the odor and finding the rotting fruit. Back in the 1970s, there was a lot of study of fruit flies and a lot of theories about how fruit flies did this. They're performing advanced differential calculus in their brain to integrate the gradient of odor to actually approach or follow the gradient of odor up the gradient towards the smell. Breitenberg actually studied these brains and was trying to figure out how a brain the size of 1/100th the head of a pin could be performing advanced differential calculus, and eventually realized, surprise, surprise, that's not actually what fruit flies do. Anybody know? It's not calculus.
Is it like ants how they use the pheromones?
They're using, not pheromones, obviously in this case, but yes, there is an odor or a signal in their environment, which is the odor plume that is put off by the rotting fruit. So they're definitely detecting it, but how do you use that signal to figure out where the rotting fruit is? This is the tricky part.
They just do trial and error if they...
Of course they do trial and error, right? So they could sit there and sort of remember changes in the gradient and integrate over time and then set off towards the odor plume, but they don't. They're not passive devices like our laptops and desktops that just sit there. They're flying and they're moving around. And it turns out, if you think about it, with about 4 lines of Python code, you could write a simulated fruit fly. If this, then this. Fill in the blanks. What is the trial and error that they're doing? If it's getting stronger, as I'm moving, if the odor plume is getting stronger, then do what?
Go in that direction.
Keep doing what you're doing, right? If you're flying and the odor level is staying the same or getting worse, trial and error, turn. Repeat, 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 right? Push against the world, fly around, observe how the world pushes back. Is the odor gradient going up, staying the same, or going down? Change or not change what you're doing. Surprise, surprise, you'll find the odor plume, right? So for Breitenberg, this was an eye-opener, right? So there were all of these scientists who were very renowned in their fields who were creating these mental models of what was going on in the fruit fly, right? They're calculating these very complex integrals to figure out where the fruit is. And Breitenberg said, you don't need to, right? If you think about the interaction with the environment, suddenly things become much simpler. So he started to publish on this and wrote this book to sort of open up this idea to a general audience. So the book is called Vehicles, and he used the term vehicles because vehicles is meant to be a generic container term. So a vehicle, according to Breitenberg, could be a robot, it could be an animal, it could be a human, it doesn't matter. A vehicle is anything that can move about in its world and sense the sensory repercussions of those actions. This book is, if you're interested in robotics, I highly recommend you read it. I've just assigned the first few pages for reading for today's lecture. It's only about 50 pages long. It's written like a fairy tale. So he starts by introducing Vehicle 1, which we'll talk about in a moment. And Breitenberg describes Vehicle 1 as, imagine that you were to see this thing and it was swimming around, it would do this and do that. And then you move on and you see this other vehicle called Vehicle 2. Vehicle 2 does this, that, and the other. It's basically a story about these increasingly complex vehicles. We'll talk about the vehicles in a moment. I think in the reading I assigned you the prologue. And in the prologue there's a section called Let the Problem of the Mind Melt in Your Mind, which was his way of summing up this problem of the mind, which is the mind's instinct to build mental models, which tend to be overly complicated than what is actually going on in the vehicle that you're observing. Right? Okay, I'll leave that for you to read. Let's talk about the vehicles. Vehicle 1 is pretty simple. So it's got a main body here. It has a single wheel at the back. This wheel cannot turn. It can only spin faster or slower. On the front of the robot is a sensor, and in Vehicle 1, the sensor is a temperature sensor, and there is a wire that connects the sensor to the motor in a proportional sense, meaning that the stronger the sensor fires, the faster the wheel turns. Since this is a temperature sensor attached to a wheel, the sensor will fire more strongly when there's more heat, and the sensor will fire more weakly when there is less heat or it's colder. That's it. That's it. And even with such a simple robot, if you were to put it in a pond, I think he says in this case, you might observe this vehicle swimming around in a pond. You might say that it's restless and does not like warm water, but it's quite stupid since it is not able to turn back to the nice cold spot it overshot in its restlessness. Anyways, you might guess that it's alive since you've never seen a dead particle of matter that acts in this way. Is this vehicle restless? Is it stupid? Does it not like warm water? Does it like cold water?
It's none of those things.
It's none of those things. Why not?
It's not human.
It's not human. All right, anything that's not human has none of these properties, right? Okay, you can see where we're going with this, hopefully. Let's move on to Vehicle 2. So we're going to talk about Vehicles 2. There's a series, 2A and 2B, Fear and Aggression. Let's talk about Vehicle 2A for a moment. Vehicle 2A is slightly more complicated than Vehicle 1. It also has a body. It has two wheels at the back that can spin, but the wheels themselves cannot turn. They can just spin faster or slower. This vehicle has two sensors on the front, and now we're going to switch from temperature sensors to light sensors. The left sensor is attached to the left wheel, and the right sensor is attached to the right wheel. And there's a little plus sign here. The plus sign means that there is this proportional relationship. The stronger the sensor fires, the faster the wheel turns. Let's imagine that we approach Vehicle 2A with a flashlight from its front right. What does this vehicle do? It turns away from the light. What happens in the instant after it's turned away from the light? What happens to the two light sensors? The moment it turns. What's that?
The other one would be closer.
Well, it's turning away from the light. Oh, and this, well, it depends. If we look at this actual picture here, both sensors are moving slightly away from the light. So what happens? Turns a little bit away from the light, which means the overall firing of both sensors reduces a little bit, which means what? How does the robot react?
It just keeps going forward.
Perhaps. What happens to the wheels? Let's talk about the wheels. The values of both light sensors drop slightly. Tell me.
More slowly.
They spin more slowly, right? So it's turning away from the light, but it's slowing the rate at which it turns away from the light. And you're right, as it turns away, maybe the total amount of difference between the two light values begins to equalize, which means the curvature at which it's turning away from the light also increases a little bit, starts going a little bit more straight. Let's say it turns away from the light, and let's say these are omnidirectional lights, meaning it's still sensing the light behind it, but at a lower rate, so it slows down. Now I start chasing vehicle 2A from behind with the light. What does it do? Goes faster, right? So returning to student apartments, right? You may have another animal in your apartment that also acts like this. Turn on the lights and all the cockroaches run for the hills, right? Okay. What is vehicle 2A? What's its name? The question mark. So this was, vehicle 1A was restless. It didn't like warm water. It was quite stupid.
Scared.
Right, this is the coward, right? It's deathly afraid of light sources and will do everything it can to get away from them. Is vehicle 2A fearful? Of course not, right? It's not human, it's not an animal. It doesn't have access to those emotional states. Here's vehicle 2B, which is exactly the same as 2A with one difference, which is now the wires are crossed. The left sensor is attached to the right wheel, and the right sensor is attached to the left wheel. Let's imagine that we come at this one with the flashlight where the pointer is here. So we're coming at the vehicle now with the flashlight from its front left. What does this vehicle do?
It faces the light.
It turns towards the light. What happens in the instant after it starts to turn towards the light?
The light signal increases and speeds up.
The light signals increase and it speeds up, right? So it starts to accelerate the turn. And as it's accelerating the turn, both sensors are starting to fire more strongly. So both wheels are starting to turn faster. How does this end?
With it chasing whatever.
Chasing the light, right? If it's a naked bulb down within reach of the robot, it will smash into it and break the bulb. There's some great YouTube videos of people that have built vehicle 2B out of Lego, and that's exactly what happens. So vehicle 2B is the brave or the aggressor or the bully, or take your pick, right? This vehicle hates light with a passion and will do whatever it can to find every light source and destroy it. Does vehicle 2B hate? Of course not, right? It's not human, it's not an animal. Doesn't hate. 3A, back to ipsilateral connections. So ipsa means on the same, and lateral means side. So the sensors and motors on the same side are connected to each other. I'll go back to the aggressor for a moment. This is contralateral connections. The difference between 2A and 3A is that now we have inhibitory connections, indicated by the negative sign here, which means the stronger that the sensor fires, the slower the wheel turns. If we put the flashlight here, as you can see, it will turn towards the flashlight. Why does it turn towards the flashlight?
Because the left sensor is closer, which means it would be slower, allowing the right wheel to turn a little more. So it
Exactly, right? So if the light source is here, the left sensor is receiving more stimulation, which means it is inhibiting the left motor more, meaning the left motor slows down more compared to the right motor, which means it will turn towards the light. What happens in the instant of time after 3A starts to turn towards the light?
it'll equal out, and then it'll go towards it at a slower and slower rate.
It'll go towards it at a slower and slower rate and will eventually come to a standstill in front of the light. What happens if I pull the light away from it?
Speed up.
It'll speed up and then slow down near the light, right? So I move the light, it follows and stops and sits nearby facing the light. This is the lover. right? The system with uncrossed connections will, in this case, come to rest as it turns directly towards the source because the motor near, blah, 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 blah. In Bradenberg's words, the vehicle loves the light source in a permanent way, staying close by in quiet admiration from the time it spots the source to all future time. This is a world-renowned neurophysiologist using this very loaded language. Does vehicle 3A love? Of course not, right? Why would such a respected scientist use such loaded language? It's ridiculous, right? Obviously, this machine doesn't love or hate or is fearful or is stupid. That's ridiculous, right? Okay, second to last one, vehicle 3B. This one's a little trickier. So contra lateral connections, again, inhibitory connections, the minus signs. What happens with this one in the presence of a light source? Yep.
We'll turn away and then stop.
It'll turn away. So let's see here. Let's put the light source here, which will inhibit the right-hand side. So if the light source is where the pointer is, there's more light falling on the right-hand sensor, which means there's more inhibition on the left wheel, and you're right, it will turn away. What happens when it starts to turn away from the light source?
It'll be inhibited less.
It's inhibited less and it'll take off, right? Let's imagine now that there are other light sources out there. Let's imagine a darkened auditorium. I give each one of you a flashlight and tell you to run to a random location in this darkened auditorium and turn on your flashlight. Assuming that it was near one of you and turned away from you, and now there's little to no light shining on the sensors, it'll drive in a more or less straight line quickly. And because there's about 25 light sources out there, it'll eventually start to approach one of them at random. What happens as it starts to enter into the light cone of another flashlight?
It would turn away from it until the...
It'll turn away, it'll start to slow down first, probably, right? As light starts to fall on the sensors, the wheels are being inhibited, it'll slow down, then kind of turn, and then take off again really quickly. Yep.
What if it's directly in front of it? Wouldn't it just like slow down to the point of stop?
Absolutely. So if the light was exactly in front of it, it will slow down and eventually stop. If we're going to follow through this thought experiment, if we did this in reality, that would never happen. Why not? In theory, it would, but
You can't hold the flashlight.
you can't hold the flashlight perfectly correct, right? We're now not in cyberspace in a digital world, right? We're in the physical space where everything is continuous. There's little fluctuations in the sensors, the motors fluctuate a little bit. It drives over a little pebble, which causes a little bit of a hiccup, which gets picked up by the sensors and it twitches a little bit, right? You're never going to get perfectly clean behavior. So imagine now in this darkened auditorium, you're all standing out there with a flashlight and you're watching this thing drive around. It tends to go in a straight line until it gets close to one of you, kind of slows down, turns, and then takes off again. What is vehicle 3B? The adventurer, or according to Bradenberg, the explorer, right? It likes to fly around, but when it gets near something of interest, it kind of slows down and checks it out, turns away, and then takes off again. So here the vehicle is an explorer. It likes the nearby source all right, but keeps an eye open for other, perhaps stronger sources, which it will sail to, given a chance, in order to find a more permanent and gratifying appeasement. Is the explorer curious? Does it have curiosity? Of course not, right? Only humans have curiosity, and maybe some animals, but clearly not these things. Last one, I promise. 3C. Okay, here we go. A little bit more complicated, but certainly not as complicated as most animals and certainly humans. We still have 2 wheels, but now we have 4 pairs of sensors, so 8 total. We have 2 light sensors, 2 temperature sensors, 2 oxygen sensors, and 2 organic material sensors. So you can think of these as like the rotting fruit odor plume detectors, if you like. For each pair, there's one on the left and one on the right. And in the case of light, we have crossed excitatory connections. In the case of temperature, we have uncrossed excitatory connections. The oxygen detectors, we have uncrossed inhibitory connections. And in the organic material sensor pair, we have crossed inhibitory connections. So at each motor, if you look carefully, there should be 1, 2, 3, 4 arriving wires. Assume that all the signals that are arriving on those 4 wires are summed together. And some of those arriving signals may be negative, some may be positive, so they can kind of cancel each other out. We're going to take the raw sum, and if it's negative, the wheel will turn backwards. If the raw sum is positive, the wheel will spin forward. If the sum is kind of near 0, then the wheel will turn a little bit or not at all. So far, so good? Okay, we take vehicle 3C and we put it back in the auditorium and we throw some rotten fruit out there. Maybe we somehow make differences in oxygen concentrations. We put some heaters at different places in the auditorium, and we put some flashlights out there as well. How does this robot behave? Tricky, right? I don't know. Bratenberg did his best to have a crack at this. This one seems to, if you were to watch this robot or this vehicle in a darkened auditorium, you might say it has interesting behavior. It dislikes high temperature, turns away from hot places, at the same time seems to dislike light bulbs with even greater passion, since it turns towards them and destroys them. But on the other hand, it definitely seems to prefer well-oxygenated environments, and those containing many organic molecules, since it spends much of its time in such places, but it is the habit of moving elsewhere when the supply of either organic matter or oxygen is low. Perfect, right? Relatively interesting or rich behavior, even though this robot just has 2 motors, 8 sensors, and 8 wires. Does this robot like, dislike, and so on? Of course not, right? Okay, if I were to watch you throughout the length of your day, or you to watch each other, some days I'd see you attracted to certain rooms on campus. At certain regular intervals, I would see you be attracted to food sources on campus. And at regular points in time, I would see you be attracted to places where you can gain some rest for a few hours before starting all over again. Do you like to eat something when you get hungry, or like to sleep when you're tired? Yes, of course, right? You're different from these things. These things just look from the outside like they dislike and love and hate and are curious or bored or stupid or not stupid or what have you. We're different, obviously, right? Okay, good. I see at least one person shaking their head. Why are you different? Clearly you're different, right? Or we're different. Why? Of course, we could get into a religious discussion about this. Let's leave religion out of it for a moment.
One of the things I learned in biopsychology was that even with animals, we say that they like something or they're curious.
Yes?
We can't actually prove that by our own metrics because we define them in a human capacity.
True.
So you could say that about any living object. So
Sure.
it's like, where's the line between...
Where's the line, right? So we're projecting our own sort of biases on here, right? Like in a human sense. Does the fruit fly like rotting fruit? Whatever your favorite food is, can I say in the same breath that you like that particular food? It's different, right, when it's humans. What's the difference? more connections, right? So if you gave me permission to open your skull, or at least put you in an fMRI machine over at the hospital, you'd see a lot more than 8 wires, right? So that's it, right? We have many more wires inside, so we actually like, but these things don't like. How many wires do you need to have to qualify for actually liking or hating or loving or being curious? 80, 800, 8,000? At least 9, all right, exactly. Could you build a Bradenberg vehicle with 9 wires? Yeah, probably. If your defense, you're now defending human specialness, right? I'm trying to put you on the defensive. If your only argument is you have more wires than a Bradenberg vehicle, watch out, because that's not going to be true for much longer.
Wouldn't it also just be the conscience?
Yes, we're conscious and these things aren't, right?
Is this like a free will sort of thing?
It's absolutely a free will sort of thing, right? We're conscious and these things are not. Where in your 10 to the 14 wires is that thing? Where's the conscious circuit? Where's the free will circuit? Where's the curiosity circuit? The hate circuit, the love circuit?
I mean, one thing is these have to follow the program.
Absolutely, right? No free will here.
We can make choices.
Absolutely. We have free will, right?
You know, you may like one thing, but you don't have to go in that direction.
Absolutely. You can choose at any time you want to not follow the light. And you know exactly when you chose to make that decision.
Although we
right?
may have been pre-programmed to
You may have been
change our mind.
you may have been pre-programmed to think that you, if Professor Libet was here, right, he would say, you'd say, probably shrug his shoulders and say, who knows, right? Okay. That's why Bradenberg wrote this book. There are 2 messages, at least 2 levels of messages in this book, right? The first one is, the surface one is, if we want to build robotics, we want to build robots that are useful to get around in the world, start by thinking about the interaction, and often with only a few wires, you can get things that are interesting. Do any of you have a Roomba at home? This is basically what the Roomba does, and it was actually inspired by Bradenberg's vehicles, right? So instead of following the light gradient or the temperature gradient, you either move at random or you follow the dirt or dust gradient. Random's usually good enough, but you can also follow a gradient and everything's just fine. Amazon.com, they're now deploying robots in their warehouses to move things around. They put lines and other pheromones on the ground, and the Amazon robots follow those signals or follow those gradients to go to the book section of the warehouse or the home goods section of the warehouse and so on. You can do a lot. If you want to build practical robots, you can do a lot with things not much more complicated than Bradenberg vehicles. That's the surface message, but then the message underneath is we got it wrong for 20 years about fruit flies. We thought they were doing something much more complicated than they were. In the last 20 years, we've also realized we're wrong about a lot of higher animals as well. What about these particular higher animals here? If we actually like and dislike and hate and love, what is it that's different? Is it the number of connections? Is it consciousness? Is it free will? If you feel that it is those things, what exactly do you mean by that? And so on. Okay, you can take that with a grain of salt. Okay, so again, this connects back to the cognitive psychology part of the course where we were talking about people making mental models, and people are often erroneous in their mental models because of their perspective, right? So if we're looking at a distance at a Bradenberg vehicle and we don't know what's inside that Bradenberg vehicle or that animal or that human, we're probably going to attribute more complexity to it than might actually be inside that vehicle. So really we want to try and take an architectural perspective. If we know how the creature was built or the vehicle was built or we built it ourselves, we can start to do this thing thinking about if this sensor fires, then this wheel will turn, and over time this will lead to this kind of behavior. And if you do that enough, you start to realize that the complexity in the behavior that you see is not really because of internal complexity. you can get away with, or you can generate rich behavior in a machine by exploiting the richness in its environment. As a piece of fruit continues to rot in the corner, it will paint this room with a very complex portrait of odor gradients. There's a lot of complexity there, and a simple robot or fruit fly that turns under certain conditions and goes straight in others will trace this very complex and relatively efficient path to the odor source. So as we move forward and start to build robots, but also as we start to build software for devices which are interacting with the world, as good HCI designers, we want to think about how we can exploit the device's interaction with its environment. And if we think carefully about that interaction, we can usually build a relatively simple device that does what we want it to do. We don't have to build the complexity inside the device. Okay. So what are the implications then, again, outside of robotics when we're thinking about interactive agents in total? So an app on your phone that gives you notifications from time to time. We want to think about the richness of the environment and how that app may interact with its environment. Okay. Obviously, in order to make sure we got it right, we're going to have to test the app or the robot in its natural surroundings. Okay, we've got about 8 minutes left, so let's finish today with an in-class exercise. I'm going to ask you in a moment to turn to your neighbor, and you're going to write down a series of if-then-else statements, a nested set, which are going to fold several Bratenberg vehicles into one robot. Before we talk about the internals of the robot, let's talk about what we want to do with these robots. Let's imagine we're going to deploy a whole bunch of robots into an environment where we want them to do some automated construction. So they're going to build a moon base or a Mars base for us, and we're going to assume that we've already sent to the red planet a whole bunch of material that we've already dumped onto the surface. And the first thing we want our robot swarm to do is to start to clean things up and organize all of the material into different piles. We're going to make things a little bit easier for our robots. We're going to place lights on top of the objects that we dropped onto the surface. And we're going to drop a heat source somewhere, which is where we want the robots to collect the objects. Bring all of the objects to this heat source. And while you're doing so, avoid each other. Okay. Let's say that each robot in the swarm has identical hardware and software. The hardware is, it has a light, a heat, and a sound sensor, and a pair of each of these three, one on the left and one on the right. So our robot can sense differences in light, heat, and sound on either side of it. And we're also going to assume that the robot has a gripper so it can grab and carry the objects. Inside the gripper is two touch sensors. So when the robot knows that it's grabbed something when it hits an object, and that object hits the inside of the gripper and causes the touch sensors to fire. So in the beginning of my code here, I've got some pseudocode that says, if the gripper touch sensors are firing, I'm going to activate a particular Bratenberg vehicle, which is crossed excitatory connections using just the heat sensors. So in this 4 lines of code, for the moment the robot grabs an object, it's only going to pay attention to light, and it's going to do what in response to light? So this robot is running this software. This if statement is inside of an infinite while loop. It senses that the touch sensors are firing. It allows now the heat sensors to influence the motors and turns off the influence of the light and sound sensors. What does our robot do? goes to the heat, right? So if there's more heat on the left, the right wheel will turn, which will turn it towards the heat source that's on its left side. Which vehicle is this? Not quite. It's the bully, right? The aggressor. It's going to go find the heat source, and hopefully we put a little shield or cage around the heat source. It'll bring the object to the heat source, which is what we want the robots to do. However, these 4 lines of code are not enough, right? What should the robot do in the else statement? There's an else that's missing here, which is when it's not grabbing an object.
Go towards the light.
Okay. There's also some other clauses we need to put in here because we also want the robots to avoid each other. A little more tricky. So turn to your neighbor and see if you can start to flesh out some more of these if-then-else statements. So under what conditions should it turn on and off different Bratenberg vehicles so that it does what we want it to do? I'll give you 4 minutes for that, and we'll see what you came up with.
Why are the wiggles avoiding each other? So the other one it says so.
We want the robots to avoid themselves because they cost $2.7 million each, and it took us 17 years to get them to Mars.
So if they don't
That's
avoid
why.
each other, they would go for the same source and hit each other?
You tell me. You tell me.
Yeah, if we're missing this much money, they should keep going for durability.
Yeah, exactly.
So you need an else statement source.
Because like it would
No, it's just three jobs.
but it would seek out the source. That's true. So just have it stop and there's a light sensor.
Yeah, so if the sensors are firing do this, else will go toward the light. But that is once it's inside a grader, if you're close to another machine, turn off. Or move away.
Right, yeah, the sound, we hear the sound. So the same light out there from light, just switch to some light. Once it bumps it, grip sensor senses grab it.
Yeah.
And then it's got to move towards thing, so the avoid each other probably have to be enough to each.
I would say have that be the wow. Well, not near the robot. Determined by sound. Run these protocols. And then for the wow that was used to send the robot.
Like, the left light sensor fires and it has no item, the right motor would go, and then the right light sensor fires and has no item, the left motor would go. That would steer it towards the light source.
What's a wow?
And then that's if it doesn't. Yeah, exactly.
Yeah, but
They need
wow
to slow
is
down
see,
for any of their
next
tasks.
step of it then.
Like once they're coming closer to an object.
Because if it only does once, and we want this to continuously go. We already used
I feel like they should
the
just slow
word
down
wow.
even when they're other
Wow.
robots, just
The
in
robot's
case.
moving. Wow, its job isn't done yet.
Because I mean, if they stop around other robots, they're just going to be permanently stuck there.
Right.
So they have to slow down in that situation. I guess that's just implicitly.
That would be slower.
Okay, I think we're out of time for today, so we'll talk about your solutions on Monday. You have a quiz due tonight, and you're working on weekly report number 1. Have a good weekend.